Hello, my name is Roy Simpson. I'm a professor of mathematics at Cusumnes River College in Sacramento, California. This proof in differential calculus is for the theorem, let f of x and g of x be continuous functions at x equals a, then any arithmetic combination or scalar multiple of f and g is also continuous at x equals a. Now, if you're not too familiar with what I mean by scalar multiple, a scalar just is a constant. So really what this is saying is that if you know f and g are continuous, then f plus or minus g is continuous, or f times g is continuous, or some constant times f. That constant is called a scalar. Some constant times f is continuous. The things that we'll need for this proof, and in fact I'm going to go ahead and tackle of these. I'll tackle the middle one here, so the product of functions. What we're going to need are prerequisite skills for success here. We'll need to remember that the limit of products is the product of their limits. So as long as f and g are defined and their limits exist, then I know I can split the limit. Also, you'll have to be somewhat familiar with the concept of continuity, which is a stronger form of a limit existing. Continuity not only says that not only the limit exists, but it is equal to the function evaluated at a. So let's begin the proof here. So we'll do the proof for the product as I mentioned earlier. First thing we have to remember is that we are given that f and g are continuous at x equals a. So we're going to suppose, and that's how you kind of start every single proof, is with what you're given. So suppose f of x and g of x are continuous at x equals a. Now if this is the case, then we know first of all that their limits exist, right? So therefore, not only actually do the limits exist, but we can easily say, just because we know that they're continuous at x equals a, that the limit as x approaches a of f of x is equal to f of a, and that the limit as x approaches a of g of x must also equal g of a. That's just because they're continuous. So all I'm doing for this proof is taking what they told me is true. They said f and g are continuous functions at x equals a. So I'm using the definition of continuity here. Well, let's go ahead and play with the idea of a limit of products here, because I want to show really that the product, so maybe I'll create a new page here to demonstrate what I want to show. That's a little bit easier. And I'll just do this in red on a separate piece of paper. It's very important that you have some scratch work on the side for yourself to tell you kind of how you're going to go. That's how most proofs work, is that you have a kind of a conglomeration of scratch work that tells you kind of what you're doing. We want to show that the limit as x approaches a of the product of f and g must equal f of a times g of a. That would define for us that not only does the limit of the product exist, but the limit of the product is equal to the value of those functions at a. So we want to show that this is true. Let's go ahead and go back a page here. Switch back to my black pen. So I'll start with writing down the limit of the product. Maybe I can work with that. So the limit as x approaches a of the product itself. Let's see. One thing I know I can do is, since f of x and g of x have limits that exist at x equals a, I can split this limit. Now remember, I can only split this limit because f of x and g of x have limits that exist at x equals a. That's a very important point to make. If you can't say that, you can't split this. But they told us in the beginning f and g are continuous, therefore their limits at a exist, or as we approach a. Another thing that we know is that the limit as x approaches a of f of x, well, that's just this little statement right here. Let me highlight it for you. And we also know that the limit as x approaches a of g of x is g of a. So let's go ahead and replace these symbols with that. So we have f of a here, and we have g of a there. And of course, we now have the product f of a times g of a. Just to verify, this is exactly where we wanted to go, because we wanted to show that the limit as x approaches a of the product is equal to the function values evaluated at a. That's the definition of continuity right there. And we have just shown that through a chain of equalities here that this is absolutely true. So this chain of equalities tells us that the limit of the product is equal to the product of the functions evaluated at a. Therefore, this has been proven. QE.